To this point, our study of physics has involved just three physical quantities: mass, length, and time. We now add our fourth physical quantity, which is temperature, allowing the study of wide variety of new physical quantities that mechanics alone cannot address. We now begin by showing how differences in temperature relate to a particular type of energy transfer we call heat. We are going to discuss the connection between changes in temperature and changes in other physical quantities.
This chapter starts with the first topic, temperature and the zeroth law of thermodynamics. The basic idea of the zeroth law of thermodynamics is that thermal equilibrium is determined by a single physical quantity, which is the temperature. We begin with objects A and B in thermal contact and in equilibrium. Next, object B is separated from A and placed in contact with C. Objects C and B are also found to be in equilibrium. Hence, by the zeroth law, we are assured that when A and C are placed in contact, they also will be in equilibrium.
To summarize, the zeroth law of thermodynamics can be stated as follows.
If object A is in thermal equilibrium with object B, and object C also in thermal equilibrium with object B, then objects A and C will be in thermal equilibrium if brought into thermal contact.
To apply this principle to our example, let object A be the piece of metal and object C the pool of water. Object B then can be a thermometer used to measure the temperature of the metal and the water. If A and C are each separately in equilibrium with B, which means that they have the same temperature, they will be in equilibrium with one another.
The Celsius scale is named in honor of the Swedish astronomer Anders Celsius, born in year 1701 and died year 1744.
Originally, Celsius assigned 0 degrees to boiling water and 100 degrees to freezing water.
These values were later reversed by the biologist Carlos Linnaeus, born in 1707 and died year 1778.
Thus, today we say that water freezes at 0 degrees Celsius, which we abbreviate as 0 degrees Celsius, and boils at 100 degrees Celsius.
Our last temperature scale would be the Kelvin scale. The Kelvin temperature scale, named for the Scottish physicist William Thomson, or also known as Lord Kelvin, is based on the existence of absolute zero. In fact, the zero of the Kelvin scale, abbreviated 0 Kelvin, is set exactly at absolute zero.
Thus, in this scale, there are no negative equilibrium temperatures. The Kelvin scale is also chosen to have the same degree size as the Celsius scale.
When we write a Celsius temperature, we give a numerical value followed by the degree symbol and the capital letter C. For example, 5 degrees Celsius is the temperature 5 degrees Celsius. On the other hand, if the temperature of an object is changed by a given amount, we use the notation C degrees. Thus, if we increase the temperature by 5 degrees on the Celsius scale, we say that the change in temperature is 5 Celsius degrees, that is 5 Celsius degrees. This is summarized below.
The title of the book Fahrenheit 451 refers to the temperature that book paper burned, or 451 degrees Fahrenheit. What is the temperature in degrees Celsius? So to solve this question, we should use the equation for solving Celsius, which is 5 over 9 times the given Fahrenheit minus 32. So if we plug in our given Fahrenheit, which is 451 degrees, and if we solve for this, it will turn out to be 232.78 degrees Celsius. Tatiana is researching vacation destinations, and she sees that the average summer temperatures in Barcelona, Spain is around 26 degrees Celsius. What is the average temperature in degrees Fahrenheit? So to solve this question, we must use the equation in solving Fahrenheit, which is 9 over 5 multiplied to the given Celsius plus 32. So if we plug in the given Celsius, that is 26 degrees, and by solving this all, we will be getting the result of 78.8 degrees Fahrenheit, or when we round up, 79 degrees Fahrenheit. Liquid oxygen boils at a normal temperature at negative 297.328 degrees Fahrenheit. What is this temperature in Kelvin? To solve for Kelvin, we must first convert your given Fahrenheit into degrees Celsius. To get this, we know that the equation for degrees Celsius is 5 over 9 times the given Fahrenheit minus 32. If we plug in our Fahrenheit value, we would come up with the answer negative 182.96 degrees Celsius. Now that we have our Celsius, all we have to do is add 273.15 and we will be getting our Kelvin. If we plug in our Celsius, the answer would be 90.19 Kelvin.
Thermal expansion. Most substances expand when heated. For example, power lines on a hot summer day hang low compared to their appearance on a cold day in winter. In fact, expansion is the basis for many thermometers, including the familiar thermometers used for measuring a fever. The expansion of a liquid such as mercury or alcohol results in a column of liquid of variable height within the glass neck of the thermometer.
A vertical steel antenna tower is 200 meters high. Calculate the change in height of the tower that takes place when the temperature change is from negative 20 degrees Celsius on a winter day to 30 degrees Celsius on a summer day. So to solve for this problem, we have to find the coefficient of the thermal expansion in 20 degrees of the certain material used for the construction. So the certain material used was steel, and if we look at the table, we would get the coefficient to be 12 times 10 raised to negative 6, which is 0.000011. And the other given items are length 1, which is 200 meters, temperature 2 and temperature 1, which is 30 degrees Celsius and negative 20 degrees Celsius respectively. If we get the change in time by subtracting negative 20 degrees Celsius from 30 degrees Celsius, we would get 50 degrees Celsius. So if we input our values into our equation, which is the change in length is equal to alpha, which represents the coefficient of the material, times length times change in time. So that would be 0.000011 times 200 meters over 50 degrees Celsius, which is equal to 0.000044 meters.
Take. Good Okay. Hello everyone. Today I'll be conducting an experiment to show you heat and temperature transferring. First we'll be trying out this cutter and how it's not heated up. As you can see here, it's not heated up as I can touch it up right myself. We're going to cut this EVA foam as this is actually a very soft material that at the same time can easily cut through when it's heated up. For example, this one. See, as it only cut for about 3 millimeters deep. But then when I heat it up, we'll use this blowtorch. And we'll see how easy it cuts through this EVA foam. As you can see here, the cut isn't that clean, but it shows the melted edge. This plate is still hot, so we'll transfer the heat to this cup of water.
Conduction. Perhaps the most familiar form of heat exchange is conduction, which is the flow of heat directly through a physical material. For example, if you hold one end of a metal rod and put the other end in a fire, it doesn't take long before you begin to feel warmth on your end. The heat you feel is transported along the rod by conduction. Thus, conduction depends on the type of materials involved. Some materials called conductors conduct heat very well, where other materials called insulators conduct heat poorly. Convection. Suppose you want to heat a small room. To do so, you bring a portable electric heater into the room and turn it on. As the heating coils get red hot, they heat the air in their vicinity. As this air warms, it expands, becoming less dense. Because of its lower density, the warm air rises to be replaced by cool, dense air descending from overhead. This setups a circulating flow of air that transports heat from the heating coils to the air throughout the room. Heat exchange of this type is referred to as convection. In general, convection occurs when a fluid is unevenly heated. As with the room heater, the warm portions of the fluid rise because of their lower density, and the cool portions sink because of their higher density. Radiation. Though convection and conduction occur primarily in specific situations, all objects give off energy as a result of radiation. The heat you feel radiated from a hot furnace would reach you even if the air were suddenly removed. Just as radiant energy from the sun reaches the earth across 150 million kilometers of vacuum. Since radiation can include visible light, it is often possible to see the temperature of an object. Examples include the heating coils in a range or oven. The filament in an incandescent light bulb glows yellow hot at about 3000 degrees Celsius, about the temperature as the same as the surface of the red supergiant star Betelgeuse in the constellation Orion. The surface of the sun in comparison is about 6000 degrees Celsius. Very hot stars with surface temperatures in the vicinity of 10,000 to 30,000 degrees Celsius are blue hot and actually appear bluish in the night sky. Rigel, also in the constellation Orion, is an example of such a star. Look above and to the left of Orion's belt to see the red Betelgeuse, and below to the right to see the blue Rigel.